Hello again. In our last demonstration video, we defined our demo species object and sketched out its functionality, and began writing code that would initialize this object. That code is stored in its constructor. Let's review the core functionality of our species object we just set up. This class is responsible for implementing the key components of our eco-evolutionary model. This includes specifying the genotype-phenotype maps, simulated reproduction, and updating individuals. In this video, we will focus on specifying the genotype-phenotype map in our species class. Let's begin by revisiting the setPhenotype function. Recall that this function is responsible for determining and assigning the phenotypes of individuals based on their genotypes. Again, our arguments will be the index of the first individual whose phenotype we need to calculate, and the number of individuals for whom we have to determine a phenotype. We'll do this by creating a for loop for each of our n-phen phenotypes. For each phenotype, we'll define a pointer to the genotype-phenotype map object that is responsible for managing our phenotype assignments. This will use the base class genotype-phenotype map from the core SPEGG codebase. Then we'll call a function, referred to as a factory function, that will create the specific genotype-phenotype map for your given phenotype. Third, we'll actually invoke a function that will calculate the phenotype for our species demo species. Finally, let's clear up our genotype-phenotype map. No doubt this seems a bit cryptic to you at this stage, because we haven't defined our genotype-phenotype maps yet. However, notice that this code allows us to encapsulate and abstract away the specific details about our genotype-phenotype map, and doesn't have to expose that functionality inside our demo species object. This permits modularity, so that if later we want to add more phenotypes that are subject to evolutionary change, for example, we don't have to modify our demo species class codebase. Going back to our header directory for our demo species, we'll want to define a genotype-phenotype map class. So let's create a header file called demospecies genotype-phenotype maps.h. Now, we're interested in modeling two phenotypes, a phenotype that controls individual fecundity and a phenotype that controls individual mortality. So what we're going to do is create a class that models the genotype-phenotype map for the fecundity phenotype that inherits from the genotype-phenotype map base class, and, similarly, a class that models the genotype-phenotype map for the mortality phenotype. I'm just going to take a brief detour to show you around the genotype-phenotype map base class. If you navigate to the Add Kids directory, you'll see that there is a genotype-phenotype map class definition file. This class consists of two public methods, a factory method that creates the genotype-phenotype map, and a calculatePhenotype method that actually performs the calculations involved in the genotype-phenotype map. This method is a virtual method. It's actually defined in full and implemented by the derived classes. There are also several protected members accessible only to genotype-phenotype map objects. These are a class that describes the parameters that you will input into the genotype-phenotype map, an integer that describes the index of the phenotype being modeled among all the other phenotypes in our model, two integers that keep track of which individuals you begin your genotype-phenotype map calculations on, and finally an integer that keeps track of the number of individuals or offspring whose genotype-phenotype maps you have to evaluate. We also include a random number generating engine. Each genotype-phenotype map that we want to describe in our eco-evolutionary model will therefore carry all these components. Now, back to our genotype-phenotype maps specific to our demo species. We want the genotype-phenotype map classes to be specific to demo species. Thus, we want it to be a derived class of the generic genotype-phenotype map object. First, let's specify our constructor, which will take as its first argument the species object. But notice that what we need for calculating a genotype-phenotype map, namely a vector of genotypes and phenotypes and the input parameters, is available only in the ins class, so we'll just use the base ins object. This permits us to reuse the constructor for a fecundity genotype-phenotype map if we're interested in modeling fecundity evolution in another species. We'll next pass as our argument the first individual whose phenotype we need to calculate, and finally the total number of individuals whose phenotypes we need to calculate. Our constructor is simple enough that we can just implement it here in the header file. Keep in mind, this isn't always the best coding practice, however. So let's just assign our index case and the number of individuals whose phenotypes we need, which we're calling numKids here. Now in this genotype-phenotype map object, we'd often like to refer to the index associated with the fecundity phenotype among the list of phenotypes. So we'll create a variable called fecundity phenotype index and pass its values from the deem parameters object in our species class. Finally, we'll point to the remaining parameters involved. We'll get the parameters from our species object and store them in our parameters object. Don't worry about the details for these classes quite yet. And in much the same way, let's define our mortality genotype-phenotype map. So we can just copy and paste our fecundity definition and rename the variables and functions accordingly. Now that we've defined the header file, we'll need to specify the corresponding .cu file with CUDA code. So let's go back to our src directory tree and navigate to the demo species directory and make a .cu file called demo species genotype phenotype maps.cu. The first thing we'll need is to, of course, include the header file where we just defined the map. Now, since that header file defined the constructors, all that's left to define is the calculate phenotype method or function. This function is going to be responsible for using the genotypic values stored in the vector f genotype and m genotype to determine the phenotypic values of individuals. In video 4, we will discuss how to implement the logic of this calculate phenotype function in greater detail. Thank you again for watching, and if you have any questions, please send an email to speg-users@googlegroups.com.